Okay, hello and welcome back. In this video, we are going to cover section 10.7, introducing something called parametric equations, and this relates to plane curves. So let's look into what that means and how we can use them in order to model some physical situations. So a plane curve, you can imagine some curve that's describing maybe like a particle as it's moving over time. So it has some kind of path and a particular direction in which it travels. You can imagine some like starting point. It travels along here. There's some bunch of intermediary points, and then maybe some final point. So we can view this as a point progressing over time. This could be when time equals 0. And let's say this is when some time counter value equals 1, and maybe when that time counter equals 2. So we can describe still the xy location of these points, but we will describe them as a function of this new variable t, which we can represent as time or anything we want to. So each point in space, instead of just calling it x comma y, we can call it x of t, so using function notation, comma y of t, meaning that our x variable is defined as some function of t. Meaning a function that has t as the variable, and our y position will be also some function of t. So using this notation on this initial point when t equals 0, this would be x of 0. Whatever x is defined as, we would plug in 0 for t. This would be y of 0. Then this point we could call x of 1, comma y of 1. This would be our x value whenever we plug in 2 for t. This would be y of 2. So the main point here is that we'll define our x and our y as some function of another variable. So let's see some particular examples. So here's the text definition of a parametric equation and a plane curve. So it says, suppose x equals x of t, y equals y of t are two functions of a third variable t. We call that variable a parameter, something that will change, and we can pick particular values, and that will correspond with certain x and y values. Um, so that we define these equations as x equals x of t, y equals y of t, where t is in some interval. So we call these parametric equations. And the whole graph that is mapped out as we plot all of the points will be what we'll call a plane curve. So let's look at an example. We can produce the graph and see how it forms over time. So they give us in example 1 a parametric equations where x of t is defined as 3t squared, y of t is defined as 2t, and we're told that t is varying between -2 and +2. T will take on values in that range. So it's asking us to graph this curve so we can see what it looks like. It's probably hard to tell just by looking at these definitions what kind of shape it will make. So it's helpful to produce a table of values. We can pick values of t, and I'm going to pick them in this given range. So t is between -2 and +2, so I'll choose -2, -1, 0, 1, and 2. Then we'll plug this into our two definitions to find out what our x coordinate will be. That will be x of t. Then we'll plug that t value into our y definition, and then that will give us our xy coordinate pairs. So when t equals -2, I would find x of -2. So 3 times -2 squared. -2 squared would give us +4, so 4 times 3 would give us +12. And then y of -2 should give us -4 if we plug in -2 for t. So that means when t equals -2, we would have the point 12, -4 on our graph. Let's do the same for -1. 3 times -1 squared will just give us +3. Then 2 times -1 gives us -2. So we would have the point 3, -2. When we plug in 0, that will make both x and y 0. 3 times 0 squared is 0, 2 times 0 is 0. Then if I plug in +1, 3 times 1 squared is 3, 2 times 1 is 2. Then if we plug in +2, that will be 3 times 4, so +12, and then 2 times +2 will give us a +4. So let's see what this will look like. We'll plot the xy values. Oh, let's give these other coordinate points. This would be 0, 0. This will be 3, 2. And this will be 12, 4. So let's plot these in the order as t is increasing. So the first point that I'll plot is 12, -4. So it would be all the way up at 12, down at -4, somewhere roughly about here. Then we would move to the point 3, -2. So over here. Then the point 0, 0. Then the point 3, +2. Then the point 12, +4. So we started at the bottom and then curved towards this middle point and then went back out. We actually get this sideways parabola. So we usually designate the direction that this is being traced out. So I'll put little arrows on the curve. So that will be the plane curve with our given direction. So if you're given a pair of parametric equations defining x and y as some variable, usually t, but it could be anything else. And if it's asking you to graph, it's helpful to create a table like this. Just pick some t values in the particular interval that they give you, then plug it into your x definition for each t value, then plug each t value into your y definition, and then we can get a series of coordinate points. And then if you plot them in the particular order that they're produced, you'll see the direction of the curve, the way in which it gets drawn out. We can also try to find the regular rectangular equation of a curve that's defined parametrically. Let's take that previous example that we just saw. So they said that x of t was equal to 3t squared and y of t is equal to 2t. So kind of like solving a system of equations by substitution in a way. Let's take our expression for y. This tells us that y is equal to 2t. Let's solve this for t. I would just divide the 2 over, so t would equal y over 2. I can then take this and plug it into the x equation. So I can replace t with this expression, since we're saying that x is equal to 3t squared. Let's plug in y over 2 for t, so 3t or 3 times y over 2 squared. So that gives us this statement, x will equal 3 times y squared over 4. Which makes sense because we saw a sideways parabola, so we should expect that y would be squared and that x would be to the first power. So this is called eliminating the parameter. There's multiple ways to do that in different situations. We'll see a different one in our next example. But if you have something like this and they want you to produce the rectangular equation or eliminate the parameter, try solving one of them for t, and then you can plug that into your other equation. We basically are trying to eliminate the t and just get it in terms of x and y. So try solving one for t and then plug into the other equation, and you should get some final equation that just involves x and y. So let's see in example 2, we'll see one that is defined by some trigonometric equations. So they ask us to find the rectangular equation of the plane curve whose parametric equations are x of t is equal to a times the cosine of t, and y of t is equal to a times the sine of t. So we want to turn this into just some equation with x and y. This should probably remind you a little bit of polar equations, like equations in polar form. In a sense, we were doing parametric equations at that time too, just kind of by a different name. Since we have sine and cosine, there's some identities that we can use. Let's solve each of these for their trig function. Like I could say that the cosine of t would equal x over a. And here I can say the sine of t should equal y over a. So we have some identities to work with. We know that sine squared plus cosine squared equals 1. This allows us to plug in some trig functions and get something that does not involve trig functions as the result. So let's replace sine and cosine with what we've just defined. Sine we've said is y over a. So this would be y over a squared plus cosine squared, that will be x over a squared, equals 1. Well, that gives us y squared over a squared plus x squared over a squared equals 1. If we multiply everything by a, and I'll write it with the x term first, we would get x squared plus y squared equals a. So we're just multiplying everything by a. It will cancel on the left side and show up on the right side. Oh, and we're multiplying by a squared. And to say that, so this will be a squared. So I can even write this out. We'll multiply the left side by a squared, it will cancel, and we'll multiply the right side by a squared. So what kind of shape of this? We can recognize this as the equation of a circle centered at the origin with a radius of a. So we'll have some kind of circle. It'll go out a distance of a in both directions. So in what direction will this be traced? If we wanted to, we could create a table of values. We can try and just see, let's think of a few to plug in. When t equals 0, what would be our starting point? If t equals 0, thinking about how this is defined, the cosine of 0 is 1, the sine of 0 is 0. So we would just get the point a comma 0, meaning we would start on the right side of this circle. Then if we plug in pi over 2, cosine of pi over 2 is 0, so our x would be 0. Sine of pi over 2 is 1, so a would be, or y would just be a. So we should be going in the counterclockwise direction. You can see which points come after the other. So I'll add some arrows showing the particular rotation. So if you have some expression, some parametric equations involving trig functions, you can try using maybe the Pythagorean identity in order to eliminate the parameter if we had to convert this to a rectangular equation. So let's take a look at part 3, or example 3. They ask us to find the rectangular equations for the following plane curves defined by parametric equations and graph each curve. In part A, they tell us that x of t is equal to a times the cosine of t, and y of t equals a sine t. That's actually the pair we were just looking at, so we can just borrow from our work previously. We said that this turns into x squared plus y squared equals a squared. But this time, they're telling us our t values are just between 0 and pi. So we'll get the same kind of curve, but it will only go until we reach an input value of pi. That means it's only going to trace out the first half of that circle that we saw. So we would still start out here on the right side, and then it will finish over there on the left side. You just get half of a circle. And it was going in the counterclockwise direction. So we do have to consider the range in which our parameter is defined. It'll typically give us some kind of interval. In part B, we have something that looks kind of similar, but we'll see how this will differ for us. So we have x of t is equal to negative a sine of t, and y of t is equal to negative a cosine of t. So let's convert this to a rectangular equation like we did in that previous example. I can solve this for sine of t, and that tells us that sine of t is equal to negative x over a. In our second equation, if we solve it for cosine, we get that the cosine of t equals negative y over a. Then let's use the Pythagorean identity. Sine squared plus cosine squared should equal 1. So our sine is negative x over a. That will be squared plus cosine squared, so that will be negative y over a squared will equal 1. Notice we'll actually get the same equation back. If we square this, we would get, the negatives would cancel, so we would get x squared over a squared plus y squared over a squared equals 1. Multiplying everything by a squared, we will get that same circle definition. X squared plus y squared equals a squared. But what would our graph look like? So we have the same condition that t is going from 0 to pi. Let's build a table of values this time. So let's take t values from 0 to pi. So let's do 0, pi over 2, and pi. That'll help us see where our curve will be traced. So we'll find out what x of t is equal to and y of t. So when we plug in 0, I'm going to look at our original definitions here. X of 0 would be negative a times the sine of 0. Sine of 0 is 0, so this will just become 0. And then y of 0 would be negative a times the cosine of 0. Cosine of 0 is 1, so that would become negative a. Then at pi over 2, the sine is positive 1, so we would get a negative a for our x value. And the cosine is 0, so we would get 0 for our y value. And then at pi, sine is 0, so we would get 0 for x. And cosine is negative 1, so we would get negative a times negative 1, which would give us positive a. So let's see what this traces out. So we would start, let's put our a's in here. This would be a, negative a, negative a, a. So we'd start at 0, negative a as our first point. Then we go to negative a, 0, and then 0, positive a. So we're starting at the bottom of the circle, and then they would trace the semicircle up to the top. So we'll get just the left side. Let's add an indication of our direction. So even though we end up with the same rectangular equation, what it traces out can be different depending on how our parametric equations were defined. So let's see an application question. So this is us using time as a parameter in a parametric equation. So they give us some parametric equations that define the path of a projectile. You might have seen this if you're taking a physics class. So they give us two equations, one for the horizontal distance. So if we have some projectile, it travels some horizontal distance, and then it has some vertical distance for each point that we can identify on there. So they define x of t as v, you can call that v sub 0 or v naught. That's our initial speed or initial velocity. So let's define that term. So the initial velocity times the cosine of the angle in which the projectile is fired times t. And then y of t is defined as negative 1/2 g times t squared, where g is our acceleration due to gravity. So that's defined as 32 feet per second squared, or 9.8 meters per second squared. Plus our initial velocity times the sine of the angle in which it's fired, times t, plus h, which is the initial height. So let's apply that to this problem. Here we have somebody is hitting a golf ball with an initial speed of 150 feet per second at an angle of 30 degrees to the horizontal. They give us a diagram. So they want us to find the parametric equations that describe the position of the ball as a function of time. So let's write out what we have. We have an initial velocity of 150 feet per second. Our angle is 30 degrees. And we can say our initial height is 0 since we're hitting the ball from the ground. So let's use our two definitions to produce our parametric equations. We're told that x of t is equal to initial velocity times the cosine of theta times t. So that would be 150 times the cosine of 30 degrees times t. Cosine of 30 is root 3 over 2, so this is 150 over 1 times root 3 over 2 times t. So we can say x of t will equal 150 divided by 2 is 75, so 75 root 3 times t. Now let's do the same for y. They said that y of t was equal to negative 1/2 g times t squared plus initial velocity times the sine of our angle times height, or times t, I mean, plus the initial height. So let's plug in what we have. We'll have negative 1/2. For g, we'll use our 32 feet per second since we're in terms of feet. T squared plus initial velocity was 150 times the sine of 30 degrees times t plus 0, because our initial height was 0. So let's simplify everything. This would become negative 16 t squared plus 150. The sine of 30 degrees is 1/2, so that'll get divided by 2 times t. So we can say that y of t will equal negative 16 t squared plus 75t. So we have two equations where if we plug in some value of t, so like some value of time, it will give us the x part and the y part of the coordinate point. So like how far it's traveled horizontally and its current vertical position, so its current height. And if we think about it in that perspective, this makes sense because this will be some linear function of t that increases over time since our ball is traveling over time. And this looks like some kind of upside down parabola, which makes sense for the height of our projectile. It will go up, reach some maximum point, and then fall back down. So now that we have this model, we have this way of describing the point in space at any given time, we can answer some questions about the position of our ball. So part B says, how long was the golf ball in the air? So we want to find the total amount of time that passes. So how can we find that? Well, the golf ball starts on the ground, it travels some distance, and then it hits the ground again. You can see that as having a y value of 0. So that means that this point will happen when y of t is equal to 0. So if we set this description equal to 0, we can solve for t, and it will tell us what time the ball has a height of 0. So let's set negative 16 t squared plus 75 t equal to 0. If we want to solve for t, we can factor a t out of this, so I would get negative 16t plus 75 left equals 0. That will tell me that t is either equal to 0, which makes sense, that's our initial point. When time is 0, the ball was on the ground. So we want the other solution after it's traveled some period of time. So our second solution would be negative 16t plus 75 equals 0. So I would subtract the 75 and divide by the negative 16. So t should be negative 75 over negative 16, which gives us 4.6875 seconds. That's the time value whenever the ball hits the ground when it returns back to a height of 0. So that means it was in the air for that amount of time. Part C asks when the ball will reach its maximum height. So when will the ball reach its maximum? Well, we're saying that this will have some kind of parabolic curve in terms of the y value. So it'll reach its maximum height at the vertex of the parabola. So let's write out our definition for y. We said y of t is equal to negative 16t squared plus 75t. So it will reach this maximum at the vertex that will be associated with some value of t. So let's remember how to locate the vertex of a parabola just by given its equation. If we have something like ax squared plus bx plus c, there is a formula for the vertex. Its x position was negative b over 2a, and then we can plug that in to find the height. So we can write that as f of negative b over 2a. That would give us the y position of our vertex. So our b value is 75 and a is negative 16. And this would be our t value that we're looking for. And then this would be y of t. So that would tell us the actual height that it reaches. So first, let's find what time this occurs at. This would be negative b over 2a, so negative 75 over 2 times negative 16. This gives us 2.34375 seconds. That will be the time that it reaches its maximum. And then it also wanted the maximum height that it would reach. So we'll get that just by plugging this t value into our equation. So it would be negative 16t squared, so 2.34375 squared, plus 75t, so plus 75 times the same value, 2.34375. Plug all that in, and you should get 87.89 feet. That will be the height that it reaches. Part D asks us what is the distance traveled. So let's use our definition for x. And we will know the distance that it traveled again by using this second point where it hit the ground. If we plug that into our x definition, that will give us this horizontal value at that given time. We know it hit the ground at 4.6875 seconds. Let's write that here. So that will be our t value. And we had x of t defined as 75 root 3 t. So let's just plug that in for t. So we would get 75 root 3 times 4.6875. That gives us 608.92 feet. So we can use the x part of our parametric equations, given some value of time, to find out how far it's moved horizontally. How far has it traveled? So once we have our parametric equations defined, we can answer all kinds of questions about the location, either horizontally or vertically, at a particular point in time. Or we could find Conversely, we can find the point in time in which we have a particular attribute. Okay, the last section has us find parametric equations for plane curves defined by rectangular equations. So example 6 asks us to find two different pairs of parametric equations for this function y equals x squared minus 4. So some upward-facing parabola. So we're free to define this in any way we want to. One of the simplest things we can do is just call x of t just equal to t. Just whatever the t value is, that's what our x value is. In that case, y of t would just be t squared minus 4. We're replacing x with t. So that could be one set of parametric equations in terms of t that defines the same shape. We could also choose something like x of t equals t cubed. So plug that into our equation for x. Then we would say y of t would be t cubed squared. So those exponents will multiply. We'll get t to the 6th power minus 4. So another pair of parametric equations. We couldn't use t squared because t squared would not allow us to have any negative values of x. But if we look at just the graph of this original equation, it's some upward-facing parabola shifted down 4 units. So something like this. So we need to be able to have negative x values. That's why we couldn't use x equals, or x of t equals t squared. That would only produce positives. By setting it equal to t cubed, we're able to get all possible values. Another way to say that is the range of t cubed is negative infinity to positive infinity. It doesn't introduce any restrictions, whereas the range of t squared would just be the positive values, 0 to infinity. So let's see another example with a familiar object we saw recently. This will be the equation of an ellipse. We can convert this into a set of parametric equations. Oops. So they give us this equation x squared plus y squared over 9 equals positive 1. I can view that as x squared over 1 equals 1. So this is the equation of an ellipse. It's centered at the origin. It has a vertex 1 unit to the left and right of its center point, and vertices 3 units above and below the center point, since we have 9 under the y term. So we have some kind of curve like this. So let's see what it's asking. In part A, it wants us to produce parametric equations when the motion around the ellipse is clockwise. It begins at the point 0, 3, so we'll start at the top of the circle, and requires 1 second for a complete revolution. So if we have some kind of circular or elliptical path, then we can use sines and cosines with our x and y definitions. So let's think about our requirements. For part A, when t equals 0, we want x of t to be equal to 0. That's our x coordinate, and y of t should be equal to 3. So which trig value will become 0 whenever we plug in 0? That makes me think of the sign. The sign of 0 is 0. And we can also think, well, if we want to start at a 0 value for x, it's going to start at 0, then increase to a maximum of 1. Then it will decrease back to 0, just thinking about the x value. Then decrease to a minimum of -1, then back to 0. So it's like from 0 to maximum, back to 0 to minimum. That sounds like the sine wave. So let's say x of t will equal the sine of t. But we need to think about the period also. So I'll just leave the general term b times t, because we want to define that it will rotate around in 1 second. That will be our period. But let's first define what y of t would be equal to. We want it to be equal to 3 whenever we are at a value of 0 for t. So I know cosine of 0 is equal to 1. But we want the value to be 3 instead of 1. So let's change the value in front of the cosine to 3. We're basically changing the amplitude. We're starting at a maximum of 3, then down to a minimum, or down to a 0 value, then down to a minimum of -3, back up to 0, then back up to the maximum. That sounds like a cosine wave with an amplitude of 3. So let's find out what this b value should be. If the period is 1 second, meaning we want a full rotation in 1 second, remember our way of finding out what this value should be is to set this equal to 2 pi over b. So that means b is just equal to 2 pi. So our set of equations should be x of t will equal the sine of 2 pi t, and y of t will equal 3 times the cosine of 2 pi t. So a set of parametric equations that define an ellipse. Okay, for part B, this time it wants the motion around the ellipse to be counterclockwise. Begin at the point 1, 0, and then require 2 seconds for a complete rotation. So we can say when t equals 0, we want x of t to be equal to 1 and y of t to be equal to 0. And we want to trace things in the counterclockwise direction. So that means when we plug in 0 for t, we want an initial value of 1 for x. So that sounds like the cosine. Because it will start at a maximum, then go down to 0, then to a minimum value of -1, then back to 0, then back to its maximum. So that sounds like the cosine. So y of t, we want to start at 0. So that sounds like the sine. So going counterclockwise, start at 0, then up to a maximum of 3, back to 0, down to a minimum of 3, back to 0. So that sounds like a sine wave with an amplitude of 3. So this should be 3 times the sine of b times t. And this time they say the period is 2 seconds. They want a revolution in 2 seconds of time. So this will be equal to 2 pi divided by b. So solving for b, we get that b is equal to pi. So our two equations should be x of t would be the cosine of pi t, and y of t will be 3 times the sine of pi t. So it's helpful to, if you can, draw out a graph of your situation. If we have some kind of circular or elliptical path, we can use sines and cosines. And think about what your minimum and maximum values would be, and that can help you determine the amplitude, and it might tell you how fast it needs to spin around, and that will relate to the period of the function. Okay, that'll be it for this section. So we graphed some parametric equations by creating a table of values. We found a rectangular equation by eliminating the parameter. We saw that example of using time as our parameter. That was the golf shot projectile motion. And then we found parametric equations given some rectangular equation. Okay, that'll be it for this video, and I'll see you next time.